Hi everyone. In today's lesson we are looking at Chapter 5, Section 1, Perpendiculars and Bisectors. Our objectives are to use the properties of perpendicular bisectors and to use the properties of angle bisectors to identify equal distances. The standards are GCO 9. We start with definitions. Our first definition is perpendicular bisector. A perpendicular bisector is a segment, ray, line, or plane that is perpendicular to a segment at its midpoint. In our diagram over here, we have a segment AB that is bisected, which means that it is cut in half by a perpendicular bisector, and the midpoint is at D. And you can see over here we have a right angle created by this perpendicular bisector. Equidistance from two points. A point is equidistant from two points if its distance from each point is the same. So if you look at this example over here, point D is equidistant from point A and it is equidistant from point B. So it has the same distance from point A as it does from point B. The same thing, we can say the same thing about E. It is equidistant from point A and point B, and point F is also equidistant from point A and point B, meaning they have the same distance from both of these points. Distance from a point to a line. The distance from a point to a line is the length of the perpendicular segment from the point to a line. So if I was looking at my picture, the distance from the point to this line would be this distance right here. So from D to E. Same thing over here, distance from point E to the line is this distance here. And we can say the same thing about point F. That is the distance from a point to a line. Equidistance from two lines. The point is equidistant from two lines when the point is the same distance from one line as it is from another line. This definition is very similar to the equidistance from two points. Here's our first theorem for this lesson, Theorem 5.1, Perpendicular Bisector Theorem. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of this segment. If line CP is the perpendicular bisector of line segment AB, then CA is equal to CB. So from this picture we can see that point C is equidistant from point A as it is from point B. And because we know it's equidistant, we can say that this segment over here, CA, is the same length as CB. And we can say that because the perpendicular bisector divides the line segment AB into two equal halves, creating these two congruent lines. Theorem 5.2, Converse of the perpendicular bisector theorem. If a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. If DA is equal to DB, then D lies on the perpendicular bisector of AB. So similar to Theorem 5.1, except in this case we are saying that if we are given that DA is equal to DB and lies on this line, well then this line CD is the perpendicular bisector. Let's take a look at our first example, using perpendicular bisectors. In the diagram shown, ray BE is the perpendicular bisector of line segment AC. Our first question, what segment lengths are equal? Well, since we know that BE is the perpendicular bisector of this line AC, then we can say that AE is equal to CE. So the perpendicular bisector cuts this line in half and these two lengths are equal. Because B is on the perpendicular bisector of AC, you can also use the perpendicular bisector theorem to conclude that AB is equal to BC. So we know that since point B is equidistant from A and C, these two lines are equal as well. Part B, we're given that line segment AP is congruent to line segment CP. What can you conclude about point P? Because AP is congruent to CP, so line segment AP is congruent to line segment CP, we can say that AP is equal to CP. And then using the converse of the perpendicular bisector theorem, we can conclude that P lies on BE. So if I were to extend this line BE all the way up through point P, it would divide this point P in half, and then we would know that, and we know that it is on the perpendicular bisector because we are given that this line AP is congruent to the line CP. Going back to theorems, this time we're looking at the angle bisector theorem. If a point is on the bisector of an angle, then it is equidistant from two sides of the angles. That means if the measure of angle BAD is equal to the measure of angle CAD, then we can say that DB is equal to DC. So in this example over here, we're given this angle BAC, and it is bisected. Remember, bisect means to cut it in half, so it is bisected by the ray AD. And so since it is bisected, then angle BAD, this angle right here, is equal to angle CAD, and the sides opposite these angles are also equal. Theorem 5.4, converse of the angle bisector theorem. If a point is in the interior of an angle and is equidistant from the sides of the angle, then it lies on the bisector of the angle. If DB is equal to DC, then the measure of BAD is equal to the measure of CAD. So going back to our idea of opposite angles, if I know that this measure is equal to this measure, then I can say that the angles across from it are equal to, and we know that it is an angle bisector over here because these two angles are equal and these two sides are equal. Example number 2, using angle bisectors. So in this case, we are given a baseball field, and it says, use the diagram of the baseball infield shown at the right. What can you conclude about the measure of angle SHF? Well, let's first find where SHF is. SHF is this angle over here. And we need to figure out what this angle is. So from the diagram, you know that point S is in the interior of THF. So if I were to go from T to H to F, it's this angle over here, and point S is inside this angle here. And we are also given that ST is equal to SF. So from the converse of the angle bisector, which says that if these two sides are equal, then the angles opposite are equal, we know that S lies on the angle bisector of angle THF. So this line over here is our angle bisector. And an angle bisector divides an angle into two congruent angles, each of which has half the measure of the original angle. Well, our original angle we know is 90 degrees, so then the measure of angle SHF is 90 divided by 2, which is 45 degrees. So from this information, we can conclude that the measure of angle SHF is 45 degrees. Now it's your turn. Please answer checkpoint problems 1 and 2 in your Google Doc for your assignment tonight. So checkpoint problem number 1. In the diagram, line segment PQ is congruent to line segment RQ. What conclusion can you make about the point Q? Can you conclude that S is on the perpendicular bisector of line segment PR? Explain. Checkpoint problem number 2. In the diagram, D is on the bisector of angle ABC. What is DC? Explain. For this question, they're asking you what is the value of DC and how do you know or how did you get that value? I look forward to reading your answers. See you soon.